Hi, my name is Bethany Wright. Today I'm going to be going through problem 10.4 of Elements of Chemical Reaction Engineering, 4th edition. So I'm going to start off by reading the problem, then we'll dive into the solution. So tert-butyl alcohol, TBA, is an important octane enhancer that is used to replace lead additives in gasoline. TBA was produced by the liquid phase hydration, W being water, of isobutene, I, over an amberlist 15 catalyst. The system is normally a multi-phase mixture of hydrocarbon, water, and solid catalyst. However, the use of co-solvents or excess TBA can achieve reasonable miscibility. Then it gives us the reaction mechanism right there. Again, the I stands for isobutene, S is the solid or surface catalyst, W is water, and then TBA is our tert-butyl alcohol. So we're going to be doing part A, and that asks us to derive a rate law, assuming that the surface reaction is rate limiting. So we're going to start off by looking at the mechanism for production of TBA and writing the rate law for each part of the mechanism. So first, the reaction and rate law for adsorption of isobutene over the Amherst 15 catalyst is as follows, and you can see the first reaction in our mechanism, and then here's the rate law for that. So it's saying that the rate of disappearance of ADI is the adsorption of isobutene, equals little ki, which is the rate constant for the forward reaction of isobutene. Ci is the concentration of isobutene, Cv is the concentration of vacant site, Cis is the concentration of site filled with isobutene, and then big Ki is the equilibrium constant of the adsorption. Similarly, for the reaction and rate law of the adsorption of water over the Amherst 15 catalyst is the second equation in that, and we can write the rate law as follows, replacing the I subscripts with W to signify water. Third is our reaction and rate law for surface reaction in the catalyst, and this is the one in this problem that we're going to be looking at as the rate limiting step. So our reaction here, the rate of disappearance of the solid equals the rate constant for the forward reaction times the concentration of a site filled with water times the concentration of a site filled with isobutene minus the concentration of the vacant site multiplied by the concentration of TBA in that site over the equilibrium constant of the adsorption. And then finally, we have the reaction and rate law for the desorption of TBA from the catalyst, which is our final reaction in the mechanism, and that can be seen here. The rate of disappearance for the desorption of TBA equals the rate constant for the forward reaction times the concentration of TBA that the site is filled with minus the concentration of the vacant site multiplied by the concentration of TBA, and that's all over the equilibrium constant of the desorption. So we know the surface reaction is the rate limiting step, and the specific rate constant for adsorption and desorption are seen to be very high, which this allows us to then modify the rate laws. First, we're going to modify the absorption rate law for isobutene, saying that over K1 equals 0, rewriting it, and then just simplifying it to solve for the concentration of the site filled with isobutene. Now we're going to do the same thing for water, and so doing each of these, solving for the concentration of the site, amount of the site filled with the certain chemical will allow us to plug them in and simplify the rate law in the future. So we're going to do the same thing for water. Concentration of the site filled with water equals the equilibrium constant for the absorption multiplied by the concentration of water multiplied by the concentration of the vacant site, and then modifying the desorption rate law for TBA yields the concentration of the site filled with TBA equals the concentration of the vacant site multiplied by the concentration of TBA all over the equilibrium constant for the desorption. Alright, now we can rewrite the rate law for the surface reaction. This we wrote above, and we are going to plug in values for the concentration of different chemicals in the sites, and then simplifying that yields this, which is we're going to call our equation 1. Now, the overall partial pressure equilibrium constant can be written as Kp, and this will just allow us to, again, further simplify the rate law down the line. So we know that the total concentration on the surface of the catalyst remains constant. So this is saying the concentration of isobutene equals the concentration of vacant site plus isobutene in the site plus water in the site plus TBA in the site. And we can rewrite that using these values that we modified our equations for above to get this, and then we just simply solve that for CV by taking out the k's. So we have 1 plus that, and then just flipping it over to the other side. Finally, we are going to take equation 1 that we solved for earlier and throw in our CVs. So this allows us to get this equation, and then here we're going to solve for little k, and then use our equation for the overall partial pressure equilibrium constant, Kp, down there, and that's our final rate law when the surface reaction is the rate limiting step. Alright, thank you.